Hi, I am Valentin Roland, and today I will talk about how we can use the massively parallel compute resources of modern graphics hardware to accelerate propositional model counting. This is joint work with Johannes Fichte and Markus Hecher. First of all, let me quickly remind you of what the model counting problem is. I assume you are familiar with the subproblem that asks for a given propositional formula whether it is satisfiable or not. The model counting problem is the associated counting problem, where instead we want to know the number of satisfying assignments. Of course, naively, we could just write down a table of every possible variable assignment and count up the number of satisfying ones. However, this table grows exponentially in size with the number of variables and thus is not feasible in practice. It turns out that propositional model counting is even harder than SAT. Fortunately, a number of practically quite successful algorithms have been proposed to tackle this problem. But why is accelerating model counting even interesting? Well, especially weighted model counting, which is an extension of model counting, has received quite some interest. A range of practical applications have been modeled as weighted model counting problems, like reasoning in Bayesian networks, where a faster model counting means a faster inference process, or consider combinatorial designs, where faster counting enables faster exploration of the design space. Another interesting application is reliability estimation in power grids, where of course we want quick feedback of the reliability of such networks. So in this talk, I will first introduce a model counting algorithm that is suitable for implementing on graphics processing hardware. Then I will go into some improvements we have made in our GPU-based model counter over its predecessor and evaluate their performance impact in detail. Then I will give a short overview of 3D composition libraries that are used in a step in our algorithm. And lastly, I will show the overall performance results of our new solver and compare to other state-of-the-art systems. So let's dive into model counting on GPUs. We start with a graph representation of the input formula called the primal graph. In the primal graph, vertices correspond to the variables in our input formula, and two variables or vertices are connected if they occur together in some clause of the input formula in conjunctive normal form. So consider the three clauses of our example formula introduced previously on the bottom right, and on the left you see the corresponding primal graph. As a second step, we construct a so-called 3D composition from the primal graph, where the 3D composition is a tree whose nodes are labeled with sets of vertices of the original primal graph, which we refer to as bags. And we impose some additional requirements with regard to this labeling with bags for it to be a valid 3D composition. So first of all vertices of the original primal graph must occur in some bag of the 3D composition. Then, if two vertices in the original primal graph are connected by an edge, they must occur together in some bag of the 3D composition as well. And lastly, if a variable occurs in the bags of two separate nodes in the 3D composition, then it must also occur in the bags of any nodes that lie on the path between the first and the last node, or the initially chosen nodes. And this effectively ensures that variables always occur in connected areas of the 3D composition. To obtain a model count for the input formula, we can leverage this 3D composition in a dynamic programming algorithm. There, we only have to consider a subset of variables at a time. To see how this works, let us have a look at a small example. We start at our first node T1, which is labeled with variables A, B, and C. There, we construct a result table over these variables, where we store satisfying assignments with respect to the covered clauses by A, B, and C. So in this case, we only consider the first two clauses of our example formula, because they are covered by variables A, B, and C. So we store this table and then proceed to our next leaf node, T2, which is labeled by variables A and D. So this covers the third clause, A or not D. Again, we construct a result table and store it as an intermediate result. Now in the dynamic programming step, we join these child tables together and project away any unused variables. So in this case, only variable a remains. Finally, we sum up all entries in our root node to obtain the final model count, in this case 7. Our work is based on GPU-Z2, which implements this approach for general-purpose graphics processing units. They use the OpenCL framework to leverage the massively parallel compute capabilities of these devices. They also introduce binary search trees to only store satisfying assignments, and we will refer to this data structure as tree in the following, as opposed to storing an array of all possible assignments. Furthermore, we use the CUDA framework as opposed to OpenCL in our implementation. Now that you are familiar with the basics of applying dynamic programming to model counting on graphics hardware, let us now dive into some improvements we have made over previous GPU-based model counters. As our first addition, we introduce a compact storage format for clauses that enables quick satisfiability testing on the GPU. This format exploits that in practice we operate on 3D compositions of bounded width. The width of a 3D composition is the size of its largest bag minus 1. Now let me demonstrate how this encoding works using an example. Consider the assignment A over variables a, b, c, and d. To encode this compactly, we first have to impose an ordering on these variables. In this case, I chose a, b, c, and d. This allows us to write clauses as sequences of literals. The sequences of literals can be encoded as a combination of two bit vectors, the first of which is the occurrence vector, where a bit position corresponding to a variable is set to 1 if this variable occurs in this clause. This is accompanied by the sign vector, where a bit position corresponding to a variable is set to 1 if that variable occurs in a negated literal. Now the assignment is encoded as a bit vector as well, according to this ordering. Finally, by computing this expression, we obtain another bit vector. If this bit vector is non-zero, then we know that this assignment does in fact satisfy the clause. But for the third clause, we obtain a bit vector of all zeros, so this assignment does in fact not satisfy the third clause. So these two bit vectors can be calculated once per 3D composition node before invoking a GPU program. Further, since we operate on 3D compositions of bounded width in practice, the length of these bit vectors is bounded as well. So in practice, a 64-bit unsigned value suffices to encode a bit vector for a clause. And this effectively allows us to implement this expression shown previously using only two bitwise instructions, an XOR and a bitwise AND instruction per clause test, which is very efficient to do on GPUs and also ensures coherence between threads. Furthermore, we have added a caching scheme for result tables. You see, usually GPU memory is much more limited than main memory on big server machines. So in order to solve larger instances, we have to swap out intermediate results to main memory. However, for larger instances, this can lead to many data transfers between GPU and main memory, which are quite costly. So let's consider what happens without a caching scheme. We start by solving the first 3D composition node, generate a result table in GPU memory, and then we have to transfer it back to main memory for intermediate storage. Then we move on to the second 3D composition node. Again, a result table is generated, which is immediately transferred back to main memory. Then, in the join step, both intermediate results have to be transferred to GPU memory in order to generate the third joined result table, which is then transferred back to main memory for final output. In contrast, with global caching enabled, data transfers are avoided wherever possible. So let's consider what happens with global caching enabled. Again, we generate the first result table, but since there's still plenty of GPU memory left, we mark it as cached and just proceed to the next node. Now in the join step, the predecessor results already reside in GPU memory, so we avoid this data transfer altogether. Only for outputting the final result, the table of the root node has to be transferred to main memory. So this would be the ideal case of avoiding all data transfers. But how does the addition of a caching scheme impact solver performance in practice? In order to evaluate that, we use a family of benchmarks based on the model counting competition of last year. where in most comparisons we use track 1 of the model counting competition, and in the final comparison with other solvers, we add track 2 as well to obtain a larger set of instances. Track 2 is originally weighted model counting, so in order to make both tracks coherent, we have stripped variable weights from the second track. On the right, you see the approximate distribution of tree width across these instances. Of course, we first have to validate the claim that a significant portion of the runtime is actually spent in memory transfer. Thus, this histogram shows the ratio of GPGPU time spent in the memcopy function in either direction, when either using the array or the more compact tree data structure. For many instances with the naive array data structure, as much as 80% or more is spent in memory transfers. The more compact tree data structure mitigates this somewhat, but still the majority of instances spend at least 40 to 50% of their runtime in memcopy. So there's significant potential to optimize there. So now we compare this distribution with and without caching enabled for both the array and the tree data structure. Note that the total number of instances is different in both histograms because we only consider instances which run at least 5 seconds in one of the configurations, for the comparison to be meaningful and not be dominated by constant setup costs. With the array data structure, we see a significant benefit of employing global caching. I'd like to especially point your attention to the blue bar on the left that shows that now a portion of instances spends less than 10% of their runtime in memcopy. So these are the near ideal cases I was talking about earlier. But we also see a general shift towards a lower ratio of runtime spent in memcopy with the larger instances. The same is true with the tree data structure, which already is more space efficient, but again we see a general shift towards a lower ratio spent in memcopy. Now, since we aim for efficient hardware utilization, we will also evaluate the impact of a CUDA driver feature called pinned memory. This allows us to allocate memory in a fixed physical location, as opposed to it being swappable by the operating system. And this allows us to use the direct memory access facilities of the GPU to copy data without involvement of the CPU at all. And this, of course, increases transfer speed, but there's also an allocation overhead associated with allocating this pinned memory. To mitigate that, we employ a sub-allocator that hands out this pinned memory from a pre-allocated pool. To show the impact of pinned memory, we compare the runtimes of individual instances with and without pinned memory for both the array and tree data structure. In this comparison, caching is enabled and tree decompositions are generated with an arbitrary but fixed seed. As you can see, for longer running instances, pinned memory universally benefits performance, especially for the array data structure. For smaller instances, the allocation overhead of pinned memory sometimes outweighs its benefit, but these differences have only small absolute values. Again, the tree data structure does not benefit as much as it is already more compact than the array data structure. So far, we have introduced and evaluated 3 additions to the dynamic programming step of our algorithm. These are the compact clause form, a global table caching scheme, and the use of pinned memory. Now we will do a short survey of tree decomposition libraries, which are used in the second step of our algorithm. In general, we want to keep the width of the tree decomposition as small as possible, to keep intermediate results small as well. Remember, the tree decomposition is the width of its smallest bag minus 1. Unfortunately, finding a smallest tree decomposition is a NP-complete problem, and thus we have to use heuristics in order to solve this problem efficiently. Fortunately, this is a well-studied problem, so we will survey the winning implementations of the parameterized algorithms and computational experiments challenge in 2017, which we will refer to as Tamaki, Flowcutter, and HTD in the following. First, we wanted to verify the placement of these implementations in the PACE 2017 challenge on our own benchmark set. To do that, we allowed each implementation a runtime of up to 600 seconds per instance, and on the left we show the smallest decomposition width for every instance per implementation. As you can see, the relative performance of Tamaki and HTD matches our expectations, with Tamaki being clearly in the lead. However, Flowcutter seems to fall off on our benchmark set. However, we have to balance the time spent on finding a small 3D composition and doing the dynamic programming step. So we repeat the experiment, allowing each implementation only 15 seconds. The results are shown on the right. While Tamaki still performs very well, the lead over HDD shrinks significantly. For some instances, HDD is even the only implementation that produces a usable 3D composition. But how does the choice of 3D composition impact solver performance? In order to investigate that, we generate multiple 3D compositions per instance and compare their runtimes. In this plot, runs of the same instance are shown in the same color, while the different 3D composition libraries are indicated by different marker shapes. In general, we see that solving time does correlate with tree width, but there are sometimes significant differences between the compositions of different libraries, even if they have the same width. So this goes to show that there may be other properties aside from the tree width that significantly impact solver performance, and more research into this area could yield additional performance benefits. But in this paper, we will leave it at this brief overview. In the last section, we have seen that the choice of 3D composition plays a large role in making dynamic programming-based model counting fast. Finally, we will compare our implementation GPU-3 to other state-of-the-art systems. It incorporates all the improvements I have outlined earlier and uses HDD for 3D composition. This cactus-like plot shows the number of solved instances in our combined benchmark for each solver, given a certain amount of runtime, up to 1,800 seconds. We compare our new implementation GPU-3 to its predecessor GPU-2. We also compare to the most successful implementations of the model counting competition of last year, which are D4, C2D, and the NUS Bear Ganyak portfolio. We have also included Ganyak by itself for reference. Furthermore, as an addition to the published version of the paper, we have added the DPMC solver in its most current version of the model counting competition of this year. Lastly, we have added two portfolios of our new implementation GPU-3 and D4 and C2D respectively. While GPU-3 does not solve the largest number of instances in absolute terms, it solves most instances very quickly. This makes it suitable for use in a portfolio, like we have shown with D4 and C2D. In these portfolios, GPU-3 is chosen if the decomposition width of the given instance is below 35. And these portfolios are in fact quite competitive. Note that the new version of DPMC is actually the fastest solver in this comparison. The reasons for this are twofold. First, both DPMC and NUS Bear Ganyak include external preprocessors as part of their execution. As shown in the GPU-2 paper, the addition of such a preprocessor is likely to significantly increase the performance of the other solvers as well. Secondly, DPMC uses very efficient data structures as part of its model counting step, namely algebraic decision diagrams and tensors. So, bringing these data structures to the GPU as well could be interesting for further research. Overall, we have seen that GPU-3 is a very fast model counter that especially shines in portfolios. Nevertheless, we have seen that the potential of model counting on graphics hardware is definitely not exhausted yet. But for today, let us wrap up. Our goal was to accelerate model counting by efficiently using the massively parallel compute resources of modern graphics hardware. In order to do that, we have introduced and systematically evaluated a number of extensions over our predecessor GPU-2. These are the compact clause form, a global table caching scheme, and the use of pinned memory. Furthermore, we've conducted a short survey of the performance impact of various 3D composition libraries. In the future, aside from integrating more compact and more efficient data structures, we also plan to investigate the scalability of this approach, especially in the light of multi-GPU systems. Furthermore, it could be interesting to integrate this solver into other CPU-based solvers for solving sub-problems and thus to accelerate the solving process. Finally, thank you for taking interest in parallel model counting on general-purpose graphics processing hardware. And in the paper, you will find more in-depth descriptions and results. Now we are happy to answer your questions either via email or in the following virtual session.